I say
Yeah.
a ball is thrown from a point P with initial velocity u 12 meters per second at 50 degrees to the horizontal as shown. So, and what you did, you were asked to find the horizontal component of u, which is u cos theta. That's 12 cos theta. You got that first. In fact, I want to just give you a hint. Usually when they start out with questions like this, just suspect that you will eventually use them. It's a way of simplifying it. Some questions may not really start it this way. They will want you to figure out that you need to get this first and get the other one before you progress to the main thing, which you eventually did here. So, but if you are lucky and they begin to break it down, get this first, get the horizontal component, which of course is u cos theta, or 12 cos 50 that you did, which is 7.71, and then get the vertical component, which of course is u sin theta, or 12 sin 50, which of course is what you got, 9.91, and then show that the maximum height reached by the ball is 4.3 meters. This question is oversimplified. They're even giving you the answer, asking you to just show it, and then of course you use v squared equal to v squared plus 2as, and take your v is 0. That's 0. Okay, that's what you wrote on the other side. So you used the vertical component, 9.19.
Yeah.
Because maximum height is about rise. It's about the rise. So it's the vertical component you used, vertical component of the initial velocity, 9.91. So 9.91 squared minus 2 times 9. Actually, your g is minus, I told you, it's a rise, so it's a negative g, which is minus 9.81 times 2. That's minus 2 times 9.81. Then times the s, which is now the maximum height. So I think this thing is well structured. You were able to get it by solving for s. You got 4.3, so proven. Now this question says determine the magnitude of the displacement PQ. Displacement, do you remember what displacement is?
Yeah.
What is displacement?
Distance in direction.
Yeah, distance in a specific direction. Now you can think of it as where you are measured from where you were. Not necessarily how far you have covered before you got there. Now let me explain so that you get the difference. Look at the position A. I don't know if it's with you that I explain all that, but I will still do that. I can't remember. Another position C, then another position D. Did you see what I'm drawing?
Yeah.
Now, if an object moves like this, get to D and then back to C, assuming the distance from A to C is 8 meters, C to D is 5 meters. What's the distance covered by this object that moved from A and back to C? What's the distance covered? Yeah, what's the distance covered by this object that moved from A to C to D and back to C?
No. Oh, distance.
Yeah, distance covered.
It's what the displacement is.
Yeah, the distance is 18. The distance is the total distance. 8 plus 5 plus this other 5 to get back from D to C. But the displacement is 8 exactly. So displacement can be considered as where you are now. C, measured from where you were, A, not considering all the places you went through to get to that point. So if that is the case, if you have an object that moves around a circle from P and back to P, what's the displacement?
From where?
From this P, can you see what I drew? And back
Yeah.
to P, what is the displacement?
0.
0, because yes, it has moved the distance equal to the circumference of the circle, but the displacement is 0 because it is back to where it started. So displacement is considered as where you are now measured from where you were, of course in a specified direction. The distance can include all the places you went through. So that's something you need to consider. So in this case, it's asking for the displacement PQ. So it's just Q measured from P. Q measured from P. Did you get that?
Yeah.
So I can draw a line from here to here. That's the line we're looking at. And think about that. This will form a right angle triangle, isn't it?
Yeah.
There's something you have found already.
I found the height and I found the vertical thing.
Not well, you found the height. You have found the maximum height, and we found it to be okay. It is even given. Wow, what a question! This question is extremely simplified. Anyway, it can be helpful even if you didn't know what next to do. You can use this. So this side is 4.3. Sorry, 4.3 meters. That means we need to get this distance, and then, like you said, we can use Pythagoras theorem to get P to Q, isn't it? You need to get this distance. So let me represent that distance with a blue line. Can blue show? All right. So you need to, let me call here M. You need to find P to M. Is that clear?
Yeah.
So how do you find P to M?
It's, I thought I already have that.
No, you have the horizontal component of the, when you were saying it, I was just wondering, what are you talking about? You have the horizontal component of the velocity, which is 7.71. Horizontal component of the velocity, the initial velocity U, 7.71, which is what you drew in red, yes. But you don't have this distance P to M, or even displacement P to M. This thing you wrote in red is actually UX, U subscript X, while the other one is U subscript Y. UX for horizontal component of the velocity, UY for vertical component, like we did in the other case. So you need to find P to M. How do you find P to M? This question will not be less than 4 marks, 3 marks at minimum, because you need to do 2 steps to get it. Do you know what to do?
Wait.
Okay.
I think so. Oh yeah, I do.
Okay, go ahead, I'm waiting.
Yeah, I don't know what to do actually.
All right. To determine the displacement, magnitude of the displacement, P to Q. By the way, if they didn't say magnitude, if they didn't just say magnitude, are you listening to me?
Yeah.
you will also include its direction, which of course will be just be the angle here. You can use trigonometry ratio to find it. This angle here is not 50 degrees, so it's not this 50 degrees that the object started with. We can find it using trigonometry ratio. So you don't lose marks unnecessarily. Yes, the question says just the magnitude of the displacement, so it's only the size. But if it was this, calculate the entire displacement, you will state both the magnitude and the direction, because it's a vector quantity, so you also need to calculate this angle. We'll even calculate it. Alright, so let's go on. You need to find this distance, and to get this distance you're going to use the horizontal component of the velocity, isn't it?
Yeah.
Which is ux. What did you get for your ux? The whole
9.4.
that's the first one we got now. 7.71, isn't it?
Yeah.
7.71. 7.71 is the horizontal component of the velocity. And you know that horizontal component is not affected by gravity,
Yeah.
or there's no resultant force in the horizontal direction, I told you earlier. And because there's no resultant force in the horizontal direction, do you remember what I told you about the state of that horizontal component of the velocity?
It's not 0.
Do you mean the resultant force is 0? Yes.
Yeah.
But what can you say about that horizontal velocity? If resultant force is 0, what does that say about the velocity?
It's constant.
Yes, it's constant. So the horizontal component of the velocity is constant. Ux is always constant. Just a quick reminder. If you check the diagram where we drew all this trajectory on page 1, all the ux, having all these ones in green, all have the same value. All true, always constant. And I gave you the reason. That the reason is there's no horizontal acceleration during a projectile motion, because resultant force in the horizontal component is 0.
Yeah.
So the velocity will be 0. The horizontal component of the velocity is always constant. Sorry, the horizontal component of the velocity is constant because acceleration is 0. All right. So it's a simple s equal to speed times time. By the way, you need to find the time. Anyway, let me write the formula so that you know what you are going to do. You can use s equal to ut plus half at squared, right?
Yeah.
U is the horizontal component of the velocity, t is the time. Just for us to get the pm, we're looking for p to m, distance pm, that's what we're looking for. S equal to ut plus half at squared. And since a is 0, I told you the horizontal component has no acceleration, isn't it?
Yeah.
So the whole thing here will be 0. So that will just give us s equal to ut, because the entire thing here will be 0. Are we good on that?
Yeah.
So we need to use u and t. We already know what u is. U is the constant horizontal component, which is, you found it already. I told you eventually use all this. They helped you to get this to make your work easier. So this is the value of the horizontal component, 7.71. But we need to find t. Maybe I will just write this and probably leave it halfway and go and find t. This is 7.71 times t. So we need to find t. Okay?
Yeah.
You do get what t is. How do we get t? We can use to get t. We can use v equal to u plus at.
Yeah.
So t is equal to v minus u over a, isn't it?
Yeah.
Alright. We did all that when I was helping you to derive the formulas. V minus U all over T. Sorry, V minus U all over A. Yeah. V minus U all over A will give us T. Yeah. Am I right? Yes.
Yeah.
Okay, so just consider the rise. The rise part. The rise part. What's the initial velocity U? What's the final velocity V?
Yeah.
Yeah, I asked a question. For the rise part, what's the initial? Anyway, the final velocity is 0 now, isn't it?
Yes.
Minus, what's the initial velocity? The, the rise part. What's the initial velocity? That's the vertical component, isn't it?
Yeah.
9.91. 9.91. 9.91 all over A. And what's A?
9.81.
It's a rise. So it's a minus, isn't it?
Yeah.
Minus 9.81. So minus 9.81. That's minus G. So get the value. Get the value quickly.
The value of
T, that's T. I just wrote T here.
okay.
I just told you V is
So
0.
minus 9.91 over minus 9.81
Yep.
is 1.01. Yeah. 1.01.
Okay. Remember what we're trying to get is PM.
Yeah.
P to M. This P to M, here to here. And to do that, you have to use S equal to UT plus have it squared, which simplifies to S equal to UT. We know what U is, which is the horizontal component of the velocity, but we don't know what T is, so we need to get T first. And you use V equal to U plus AT. T is V minus U over T. V is 0, and U is the vertical component because we're treating the rise part. Alright, so T again. What did you say you got?
I got, oh my gosh.
That's disappeared. Sorry.
Yeah.
It should be 1 point something. Yeah,
Yeah, 1.01.
0, 1. Please, can you leave it to 4 significant figures because it's not the final answer.
1.010.
Okay, it's still okay. 1.010. So let's just put it to find S. So S will now be U, which is 7.71. Remember, we already know what the U is. There is times 1.01. 1.010. What does that give? Give me the answer.
Times 7.71. That's 7.78.
What did you say?
7.789.
7.789. Because that's PM. P to M is 7.789. And you know what Q to M is? So you can easily get P to Q, isn't it?
Yes.
So what is P to Q?
P to Q is
Pythagoras theorem now.
yeah, which has to be Pythagoras theorem. So that would be 4.6 squared. So that's square root of 4.3
Squared plus PM, okay.
or 7.789 squared.
Okay.
That's 8.89.
Please let me write it down. Square root of 4.3 squared plus 7.789 squared. Because this is 4.3, number is PQ we're looking for. Here is 4.3. This is what we just found now, 7.789. So use Pythagoras theorem to find PQ. Okay, so the final answer is what?
Final answer is 8.897.
So you now leave it to the appropriate number of single figures. You said 7 point what?
Huh?
What did you say it is again?
8.897.
The values given are to how many single figures?
2.
2. So what should be the answer?
8.9.
8.9. So 8.9 meters. Okay? I think that's clear.
Yeah.
Let's go to the next question. I want to explain something to you. I'm on the next page. Let's see this. It says water leaves the end of a hose at point P with a horizontal velocity of 6.6 meters as shown in figure this. The water is leaving, from this place, and once the water leaves, it will travel through this trajectory before it drops at Q because of gravity. It will travel through this trajectory. Beautiful. So point P is at a height h. The water hits the ground at point Q. The water hits here. This is the trajectory. This curve. Trajectory is the path moved by a projectile. The water hits the ground at the horizontal distance of P is 3.5, of Q is 3.5. So what's the question? Blah 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 blah. Just read the first question.
Explain briefly why the horizontal component of the velocity of the droplet of water remains constant as it moves from principle.
Why does the horizontal component remain constant? I told you these are part questions that they will ask you.
Isn't it because horizontal force of the vertical component?
Say that again. Resultant force in what component? In the horizontal component.
Yeah, horizontal.
Okay, so you're right. There is no resultant force. Let me just write it down. You're writing, okay, go ahead. There's no resultant force. Go ahead. There's no resultant force in the horizontal component. So okay, beautiful. Velocity is constant. Now, next question B. Show that the time taken for a droplet of water to move from P to Q is 0.53 seconds. Do you see the question? Show that the time taken is 0.53 seconds. Let me review the question. We're going to show that the time taken for this water to drop to this point is 0.53 seconds. What did you do? Any idea?
Well, I think so.
Okay. All right, give it a shot. Okay, beautiful.
That's correct.
Why are you doing that?
I don't know. No, I know.
Okay, tell me why you did this.
Speed is equals to distance over time.
Okay, when do we use this formula like this? When speed is constant, isn't it?
Yeah.
And you know the horizontal speed is constant. The horizontal component of the speed is constant. So you can afford to use it 6.6 divided by the
Yeah.
and the distance. That horizontal speed is constant all through.
Yeah.
In fact, please, I need to emphasize this so that you will, all of these things will be clear. When at this point, when it just starts falling, when it, you see the jet water was just released here. This is the horizontal component 6.6. The vertical component is 0 here, and then it start moving. The horizontal component stays the same value 6.6, but the vertical component start increasing gradually. It gets to another position. The horizontal component stays the same as 6.6. I told you, doesn't change. Vertical components start getting bigger until it hits here. Horizontal component also stays the same as 6.6. Let me now trace this thing, make it bigger. Oh, it's too big. Now vertical components got to the maximum. See this thing I'm writing here, you may need it to the subsequent work. So you will notice that the horizontal component all the same. Okay, I can even write those values. 6.6 meter per second, 6.6 meter per second, all through 6.6 meter per second, all through. It didn't change. The one that started getting bigger, you know, it's a fall. You know, when something is falling, it's accelerating, isn't it? From 0 vertical component at that instantaneous rest, from 0 value of vertical component of velocity, it will be increasing gradually, acceleration until it becomes maximum just before it hits the ground. Anyway, all of these ones are uy getting bigger. Uy is the maximum. Okay, I said all of that because I'm going to refer to it soon. So that is the principle you apply, because in all cases it's a constant velocity, and since we know the distance, to find the time we just say distance over time, and distance over speed.
Yeah.
Because velocity is distance over time. Please use standard symbols. Let me write this your equation. V is equal to S over T. So T is equal to S over V. Alright. So proven, the distance is 3.5, the time is 6.6, so it's proven as given here. Distance 3.5 times 6, distance 3.5, speed is 6.6. Okay, so it's proven. All right, next question. Calculate the height. I need to say something about this because I have not pointed it out. Are you listening to me?
Yes, I am.
Now, I always fight with students or argue with them each time I say this. No student has ever believed me. I had to even have to carry out the experiment so that they will believe. A crude one. See, can you see the diagram I'm pointing at?
Yes, I can.
If you leave an object to drop freely, I mean drop by itself from here, to drop, to get to here, I will call here M. Are you seeing, did you see where I wrote M?
Yeah.
I left the object to drop freely from P to M. Drop, free fall. It dropped freely from P to M. Now, when you project an object, maybe you projected it with an initial speed horizontally and then it falls. Whether you projected it with a fast speed then it falls like this, or a lower speed then it fell like this, or a much higher speed then it fell this way, much higher speed, it fell this way, or slower, it fell this way. In fact, no matter the speed with which you projected it horizontally with, it will get to the ground at the same time as if you left it to fall freely. Please let me emphasize what I'm saying. So it doesn't matter all these distances you're seeing here, whether the one in red, in yellow, all these lines I'm drawing, or the one I'm going to draw in blue, so long as it started horizontally initially and then drops, or even a smaller one, I'm going to draw in black, no, maybe red, sorry. All of these things will touch the ground. I now have different situations, 4 different situations. In fact, actually 5. 1, 2, 3, 4, and the one that was just dropped freely. They will touch the ground at the same time.
Like in the same amount of time.
Yes.
Even with greater distance.
Oh yes. Do you know that without greater distance, they would have been traveling with higher speed? They must have come out of the hose with a higher speed for them to travel a greater distance. But,
really?
yes, but they must hit the ground at the same time. So if you allow an object, this is this same object or the water, the droplet of water, to just fall freely, free fall, and then hit M. And all these other ones, the one in red, the one in black, the one in yellow, and the other one in blue, all of them will get to the ground at the same time. Nobody has ever believed me. I know you are doubting it, but that is the
So what the time?
you can. So we will use the principle that they will get to the ground at the same time to find the time that it actually got to Q. So just calculate if it was dropped freely.
Oh, like.
Hmm?
Okay.
If it was dropped freely, what would be its initial speed if it was dropped freely?
Initial speed.
Yeah.
0.
0. Good. So if you're going to drop it freely, the initial speed here will be 0. So you will be 0 here. Final speed is what you're going to calculate here. I can write it in red. So find out final speed if we need it at all.
Okay.
And of course, you know G is A is G. It's a fall, so A is positive G.
Okay.
So I can see what you did to find the V, that's its final speed here. What you did was you used V is equal to U plus 80. V is the final speed just before it hits the ground if it was dropped freely. It will spend the same time as if it was projected to take this trajectory, or this trajectory, or this trajectory, or even the other trajectory. They will all get to the ground at the same time. So V is the final speed just before it gets to the ground. A is G, U is the initial speed, which of course is 0 if it was dropped freely. So it starts with an initial velocity of 0. Okay, so that's what you did here. V equal to U plus 80, and you were able to get V to be 0, which is U plus 9.81, which is G, times T, which is 0.53. Remember, we already told that it takes 0.53 seconds to hit the ground. Show that the time taken for the droplet to move from P to Q is 0.53 seconds. This same time, P to Q, is the same time if it was dropped freely to fall by free fall. So that's the time. And you did that, and you were able to get V to be 5.199 meter per second. That's correct. I think, but to get h, because we're looking for h actually, to get h, we need to use an equation that has distance. H is about distance. And I'm happy that you started with v equal to u plus 80 to get the v first, because we need it in this equation that you use v squared equal to u squared plus 2s to get the h, which of course is s. So you substituted v squared is equal to u squared plus 2as. V squared is the 4.199 squared plus u squared, which is 0 squared, plus 2 times 9.81 times s, which is the height we're looking for. This question requires a number of steps, but it's good that you knew that you needed to find v first. That's a very intelligent one. So v squared is equal to u squared plus 2as. 5.199 squared equal to 0 squared for u, plus 2 times 9.81 times s for the height we're looking for. And then you were able to simplify. You got s, which is the height, to be 1.38. So the height is 1.38 meters. That's beautiful. Okay, so from what you can see, for the movement of a droplet of water from P to Q, state and explain whether the displacement of the droplet is less than, more than, or the same as the distance along its path. So what did you say? What do you think? You know, the displacement is just this straight line from P to Q, is it not?
Yeah, so it will be less than.
It will be less than the trajectory, which is the
Yeah.
curve, P to Q. So state and explain. State and explain.
Is it because I know why, but I don't know how to say it.
Because the curve P to Q is, the curve is the distance. The curve P to Q, which is the distance, you can put it in bracket. No, put P to Q, the P to Q, then the bracket distance, or whichever you want to write it, because the curve P to Q, which is distance, is longer than the straight line. In bracket P to Q, or whichever way you want to write it, which is the distance. The curve P to Q, which is the distance, yeah, is longer than the straight line PQ. PQ, just write it below, just use this small space to scribble it. PQ, which is the displacement. Which is the displacement. All right. So, what does this say? This one say? Read the final question.
Calculate the magnitude and distance of the droplet of water that is
From P to Q. The magnitude of the displacement.
So is that not like Pythagoras theorem?
Beautiful.
didn't know
Yeah. So we just magnitude of this displacement PTQ. We know this height. We know
that.
this this path. So to get P to Q, just like saying we know PM, we know MQ, you can use Pythagoras theorem to get P to Q. So square root of 3.5 squared plus 1.38 squared. 3.5 is M to Q, and P to M, which is the height, is what you found earlier to be 1.38.
Why is it 2 marks?
It looks so easy for it to be 2 marks, eh?
Yes.
But to come up with that is another thing. The magnitude of the displacement. Now, like I said, if they ask you for the entire thing, not just the magnitude, you need to find the angle too, is it not?
Yeah.
So let's even just add it. Direction will be what? What's the direction? That angle is called direction. Direction of that displacement.
Tan.
Sorry, I'm writing.
Oh, okay.
Direction of the displacement. Just undo. No, undo instead of erasing. Okay. Direction of the displacement is theta, which is that's this angle here. The angle, it's actually the angle it makes with the horizontal, though. Not
Oh.
the angle it makes with the horizontal.
Oh. How am I supposed to
Yeah, but you are right. You are still it's tan now. Opposite over adjacent. Just so that you need to take the right opposite. Opposite is this over adjacent. This. Because if you were using this, you would have used the wrong opposite.
Okay.
It is the
So
tan inverse of
0.6.
this over this opposite over adjacent.
So tan inverse of 1.38.
Yeah,
Over
you're right. Tan inverse of 1.38 over what?
6. No.
Tan inverse of 1.38 over 3.5, have you? You see
Yeah.
5.3.
Yes, just 5.
Okay, 3.5. Yeah. So 1.38, which is this h over 3.5. So what does that give?
21.5.
21.5. 21.5 degrees. Assuming the question required you to find both the magnitude and the direction. Alright, I think that's cool.
Yeah, very good.
Beautiful. So I just needed to give you additional information and we are done. This is applied in all this warfare. If they need to drop something at a target, imagine a bomb is supposed to be dropped at Q, right?
Yeah.
The fighter jet or whatever that is carrying the bomb must travel at a predetermined speed so that when he releases the bomb can follow the trajectory and get to that exact target. If he needs to get to a bigger target, then the fighter jet needs to move at a higher speed so that it will follow a trajectory, because it will still get to this target at the same time. I told you, whether it was just dropped without imagine the fighter jet was just hovering, not moving. Are you listening to me?
Yes, I am.
If the fighter jet was just hovering, not moving, and then the bomb was just dropped, free fall, it will take the same time as if the fighter jet was moving and then it went through this trajectory, or moving faster and then it went through this black trajectory, or moving much faster and then it went through this yellow or even the blue one. So the same time it will hit these targets. But if these targets are at different positions, then you need to know the exact speed the fighter jet has to move, so that when he releases the bomb, he can follow the trajectory and hit the exact target. Does it make a little sense?
Yeah, it does.
All right. So I think that's fine. Any question?
No.
Okay. So we have it all. All right. So I think that's cool.
Yeah.